Now on BBC Learning Zone, the Open University reveals how a simple computer can make the difference between manufacturing heaven or manufacturing hell.
She's the girl that makes the thing, that drills the hole, that holds the spring, that drives the rod, that turns the knob, that works the thingamabob. She's the girl that makes the thing, that holds the oil, that oils the ring, that takes the shank, that moves the crank.
That was a piece of World War II propaganda film to encourage the workers. However, it does contain an element of truth, in that for successful manufacturing, it's necessary to have each component when and where it's needed. The previous programme was about animal populations and natural systems. This programme is about manufacturing, man-made systems which have been designed and created by man. However, because of inherent variability, not everything is controlled. We're going to look in detail at the system and then at a model of it, in order that you can understand it and also understand how it's controlled. This is a humidification system. It's used to raise the moisture content of the air. The nozzles shoot out fine droplets of water which evaporate immediately and raise the humidity of the air. Why would you want to do that? Well, there are industries such as paper making and textiles which need a controlled humidity. The equipment that they use is made by a small manufacturing company. It's made by taking a series of processes sequentially. So we're going to call it SECPROC. SEC for sequential and PROC for processing. Now, what processes are carried out sequentially by this company? To arrive at those completed products, a large number of operations needs to be carried out. Take the nozzle. SECPROC's first task is to make the casing. It is made of brass, and the starting point is a solid cylinder that needs to be worked to produce the desired shape. It is turned on a lathe in a number of processes to a high specification that ensures regular water distribution in the finished product. Once it has been turned, threaded, bossed and checked, all in a strict sequence of operations, it is ready for assembly into the nozzle form. The casing houses an adjustable needle jet system. All the individual components must be assembled in a strict order. The tasks are different to the machining of the brass casing, but the principle is the same. Everything is achieved sequentially. The nozzle assembly operation is a small example of how SECPROC as a factory functions. And here is their first problem. To complete the assembly process, there must be stocks of all the components, no matter how seemingly insignificant they are. If the operator runs out of any single item, he is held up in his task. What's more, the lack of any component at all holds up the entire assembly process of the humidification unit within the factory. So the first thing that SECPROC wants to be sure of is that it doesn't run out of any component. It holds stocks of everything needed for assembly, so-called buffer stocks. Once the nozzle has been assembled, it must be tested, to make sure that it functions and to calibrate it to release the correct amount of water vapour. After that, it becomes part of another buffer stock to ensure that further production of a complete humidification system isn't held up. Naturally, the company is aware that it needs to hold stocks of every component of each system it makes. The mills and warehouses that Secprop supplies come in all shapes and sizes, so systems are tailor-made. If the company is to respond quickly to a customer's needs, it must keep part-finished items, which can be built into a final product. Every stage of assembly is monitored, and a close check kept on the stocks. Take the control unit. There are a large number of individual components in it, all of which need to be partly assembled elsewhere before they are incorporated into the final unit. The pipework, monitoring and control systems, and the panelling. Finally, there's another task, testing and calibration. At the end of the assembly process, the finished units join a queue for this further lengthy procedure. This single completed control unit is the culmination of a long line of tasks. Behind it, stretching back down the factory, are stocks of part-finished items, or queues of work awaiting completion or testing. Manufacturing companies have to operate in this sequential processing way. There's no other way to do it. You must hold stocks of part-finished jobs in order to avoid hold-ups with machinery and men lying idle. But all the individual managers that run Secprop have quite different perspectives on how sequential processing affects them. How would you describe the financial health of the company?
By most standards, we're in good shape. Business is increasing. We're not suffering a large level of bad debts. Raw material costs are increasing, but I think we can absorb those.
When you say most standards, it sounds as if you have reservations.
Yes, well, we are carrying a high level of work in progress at the moment, and that's costing the company a lot more money than people believe.
How does it cost money?
It ties up capital, for which we have to pay higher interest rates. We have to pay higher insurance. Also, work in progress takes up a lot of space. With all the part-finished work lying around, I think if we have less of it, we could use less space and therefore decrease our costs. I think that overall, inventory is costing us about 25% per annum of its capital value.
And you think that the inventory could be reduced?
Yes, I think it's more important than people realise to reduce the inventory levels that we have at the moment.
How do you think it should be tackled?
Well, at my last company, production was under computer control, and that seemed to work very well.
So the accountant sees part-finished work as money piled up on the shelves and wants to reduce what he sees as a waste of capital. But for this type of assembly process, is that a solution? What are the special problems affecting production?
Well, we're in the make-to-order business, so that means there's a lot of variability in jobs.
And how does variability affect production?
It means that we have to hold quite high stock levels between processes, otherwise operatives will be standing around waiting for the next job. That would cause an adverse variance. I can't just send people home when there's no work to do.
Do you think the lead time from order to delivery is rather long?
Well, I don't think it's excessive. If something's urgent, we can always put a priority tag on it and put it to the front of the queue. But I do know that the lads work more slowly if they see the buffer stocks are getting low.
There doesn't actually seem much risk of the buffer stocks running out.
Well, we run controls so that if a buffer is high, then we can work more overtime on it. And if a buffer is low, we can work more overtime on the process feeding it.
The production manager is more concerned with optimizing the manufacturing process and making the best use of an important resource, the people who actually do the work. Everyone I've met here seems cheerful. Would you say this was a happy workforce?
Yes, we have a very low turnover of staff and very little absenteeism, though I believe it wasn't always like that.
What were the reasons for difficulties in the past?
If orders are up and down, then we may have to lay people off temporarily, and that's never popular.
Do operatives get worried if the stocks are low?
If work looks a bit short, then word gets around the factory very quickly.
What would you recommend to boost staff morale?
If we had small teams working on a job from start to finish, rather than a production line, that would be much better. I've seen small teams working, and I believe that's the way we should go. People are much more committed, and they feel part of a team.
Another perspective. But is it a red herring? Would teams do anything to alleviate the problems of queues and stocks? The company's products are selling very well. Is this because they're competitively priced?
I think it's primarily because they're technically advanced and built to very high standards of quality. However, we're not complacent about this. We're always looking to improve the product.
Do you feel that there's much more scope for development?
Oh, certainly, yes. New materials are being developed all the time, and new control techniques are becoming available, some of which are useful to us.
Is there anything particularly exciting coming up now?
We're working on some printed circuitry which should eliminate a certain amount of wiring. This should improve product quality and reliability and also reduce manufacturing time.
Will that have any bearing on the problem of long lead times?
Because it will eliminate one stage of manufacturing, it should get rid of one interprocess buffer.
Advances in design, like the replacement of this wiring harness, which needs much time and effort to assemble, by a printed circuit, which is neater and can simply be slotted into a control unit, must help. But that doesn't affect the nature of the sequential manufacturing process, which will continue to throw up problems. The sales record looks good. I take it that you're satisfied with progress to date?
No, not entirely. The time that it takes to complete an order has become excessive. It should take about a week to process an order, but nowadays it's taken up to 10 weeks.
And you think that this delay affects sales?
Well, you can rely on quality and our good name for so long, but ultimately we will lose out to the competition by carrying this long delivery time penalty.
What do you think is the problem?
Well, I blame our poor estimating. If the estimation were better, we could cut right down on our buffer stocks.
And it's the size of the buffer stocks which create the long delivery times.
Oh yes, you should see the stock piled up. Everything has to wait in the queue.
What about priority labels?
Well, you can chase one or two jobs through, but you can't label everything priority.
There's one theme coming through these interviews, the buffer stocks. Finance and marketing think that the buffer stocks are too high. Finance because the buffer stocks cost too much, and marketing because the lead times are too long. On the other hand, production needs buffer stocks in order to smooth out the ups and downs. How should we decide whether SecProc should change? A clue can be found in a slightly surprising place, a shopping centre. As everyone knows, queues are part and parcel of the shopping experience, but the waiting time varies enormously. Sometimes there are few customers, the checkout staff are doing nothing, and you get served quickly. No, just a coffee, please. At other times, there are lots of people who have to wait for some time. There are two extremes. We could have lots of checkout points so that queues never develop and no one has to wait. Or we could make sure that the checkout points are busy, always with a queue because there are few checkouts. How can you choose a good working point between the extremes? Think of what happens as you increase the number of checkouts. The time a customer has to wait to be served, in other words, the average size of the queue drops. But that isn't the sole consideration in the equation. As you add more checkout points, the time that the checkout staff spend doing nothing, the so-called idle time, rises. If you could put a cost on each of these lines, then you would know the best number of checkout points. The cost of checkout staff time is straightforward. It corresponds to how much they are paid. The cost of customers' time spent waiting in queues is more difficult. If there is a choice of shop, then frequent long queues will drive the customers away, and the cost is in lost sales. So the two lines can be expressed in costs. Now they can be joined together, and we can see what happens to the total cost by adding the two separate costs together. This is the cost of the idle time when there is one checkout point, and this is the cost of the waiting time. Now we can add these two together by putting the cost of idle time on top of the cost of the waiting time. Similarly, if there are two checkout points, the total cost is this, plus this. And you can do the same for all the numbers of checkout points. The resulting line shows the total cost in money terms to the company, and the best operating point is in the region of the minimum of this curve. Many retailers, in competition with other traders, operate over here because they are more concerned with customer waiting time than checkout staff idle time. It's surprising how these ideas of queues and stocks turn up in a great variety of contexts. Here we have a different kind of stock. A stock of water, a reservoir. Rainfall is quite variable, but this stock of water ensures that householders and industry receive a constant supply. This probably represents the ultimate buffer stock. It's holding sufficient water to service consumers for months. Just because the stock is large, however, it doesn't mean that it's imprecise. The size of the facility has been carefully calculated on the basis of water use of the metropolitan district that it serves and the rainfall for the area, taking an average over decades. At the other extreme, electricity. Although a small buffer capacity is held within the national grid itself, almost all electricity is generated on a demand basis. The buffer stocks are of course held elsewhere, in the form of primary fuel, in this case coal.
We're doing 580, we'll be picking up to 600 shortly.
And these examples give us the third factor of importance, control. The control room is the most important component of the power station. Here, rapid responses can be made to fluctuations in energy demand. Similar controls are also applied to water supply. Depletion of this stock results in control over supply. Standpipes in the street restrict water use. And enterprising individuals find their own supply. Similar controls are also applied at SecProc. The controls here are putting in overtime on each process. But how exactly do we decide the amount of overtime to work? It's quite a complicated situation, which is why we have a model, so that you can try out different overtime settings and different settings of the buffer stocks to discover what will happen. It's much better to experiment with a model than with a real SecProc factory. With a model you can try lots of different runs in quite a short time. You can try settings that the management would never risk, and you can try out experiments that people have suggested. Now on the screen we can see 4 separate pairs of columns. These correspond to the queues of work in the factory. We've selected as the important points in sequential processing, first of all assembly, and then wiring, paneling, and finally test. And of course each of these columns refers to the actual processes, and the columns are the queues. So if we look in the 4th column, test, there's job number 1. Each of the jobs is given a number so that you can follow the progress of a job right through the factory. figure alongside, 4.10, is the estimated time that the job will take in test. Now, if we look further down, we can see the state of the queues. In line 28 is a reference to the number of jobs in the queue and also the amount of time that they'll take. So you can see that each of the processes has 10 jobs in the queue, except for panelling, which has 12. And the amount of workload which each process has waiting is just under 40 hours. Now, if we turn back, we can see a column containing the times at which each of the processes will end. So in this column labelled time, you can see a list starting 1, 1.04, 0.93, and you can see that the minimum in that column is 0.7. So this is the event which will happen next, because it's the shortest time ahead. What's happening here in the course of a run? We first of all set the control variables, that's the overtime control settings, and the order trigger level, and after that a whole series of events takes place. Items finish being processed and then move off to join the next queue. We're going to get out the amount of work in progress and how much it costs, and the amount of overtime which is going to be worked in order to control it. So it's one particular snapshot of the working of the system. And of course, if we want to build up a general picture, we've got to have lots of snapshots. Now, the objective that you have in carrying out a series of simulation runs is that you can build up a pattern of the effect which the control variables have on the operation of the factory. And out of that pattern, of course, you can perceive where the best operating point is. In other words, you can discover the optimal working point. There, the simulation's finished, and we can look at the results. The value of the work in progress is £147,000, and to service that work in progress for a full year would cost just about £37,000. There's no time been lost from idleness because none of the queues have gone to zero. But in line 36 we can see that it was necessary to use overtime. And the overtime cost, if this ran for a full year, would be just under £28,000. In line 37 the cycle time is 23 working days. That means that on average a job would take just under 5 weeks to pass through the factory. Well, that's how to carry out a simulation run with a SecProp model. Of course, there's more explanation in the text and on tape to assist you with carrying out your explorations of the model. Of course, one run of the model isn't enough to establish a management strategy. You need a longer run and you need several runs in order to do that. When you've used the SecProp model, then you'll be able to advance and learn how to construct your own models. And that's even more interesting than running this one.